Okay, good afternoon. Our second talk of the session is actually the same speaker we had for the first talk, but since not everyone was probably here, let me introduce Udo Hafermann from Software AG, who also serves on the OSGi Board of Directors. Udo.
Yes, thank you. Actually, two people behind this work, so myself, Udo Hafermann, and Todor Boev, we're both architects at Software AG, and Todor is co-chair of the Enterprise Expert Group. Okay, so this talk is about actors and OSGi, and the underlying, well, the question behind is how to achieve concurrency in a modular way. So, oops, I need to switch to the presentation, of course, sorry. Sorry, I made a little mistake here. Excuse me, I just made a mistake because I'm switching to the wrong to the wrong screen here. I thought I was absolutely cool, but I wasn't. So where's my, here I am. Okay, so now I can move on. So I'm going to, after motivating this, I'm going to present the actor model, talk a little about actors in Java, and go through an example and explaining along the example how our envisioned implementation of actors in the OSGi context could work. If there's time, we can look at the code. So the background is concurrency, especially because there's more and more need for asynchronous concurrency. And we do have mechanisms for communication between asynchronous participants in such a system, but they don't really handle state too well. They still require lots of coding to get the synchronization right. So anyone who's been involved with concurrency knows that it's hard to get right, the communication between threads, between the state of different services and so on. So one alternative that we wanted to investigate a little more was to use message passing instead of synchronous calls or asynchronous calls where you have locks and threads to manage the communication. So message passing is supposed to be kind of fire and forget. I've sent a message and hopefully the correct reaction will happen somewhere, but I don't have to bother about synchronizing my message explicitly in the code. And the hope is that this will enable some composition of services under this background of being highly concurrent. And actor systems are this very pure embodiment of a message passing and asynchronous computation. Who's ever had contact with actors and actor models? Okay, so that's our question behind this. Could actors help here? So what's the actor model? Actors are objects that process messages, and an actor can receive messages, and depending on the message, the actor can decide to process this in steps that consist of either sending another message or creating other actors. And the actors it creates, it can keep the address of it and can later send message to that actor. So that's the whole model. Sending messages, creating other actors, and through this concert and choreography of messages that go around, we have the meaningful behavior of the system. And state is modeled that in such a way that the actor, after processing a message, defines the next behavior it's going to apply to the next message that comes in. Yes, please.
The message consumed then, or there would be multiple actors for one message?
In the theory, I think you could have all sorts of ways, but here it's just one message to one actor, sent once, processed once, period. So that's the model. There are quite a few actor implementations in Java. We chose Akka. Akka is very rich, so it's supposed to be a complete system with complete set of functionality for everything. It's actually based on Scala, not on Java, but it has Java bindings, so you can use the Java APIs And that's what we're doing in this, in our approach. And it's actively developed. So the other systems out there might also have their merits, and some are also actively maintained, but we chose actor and didn't do a comprehensive evaluation of all systems out there. This is a very common example to illustrate how actors work, the dining philosophers. So the scenarios that you have a couple of philosophers sitting around a table, they alternate between thinking and producing wisdom, and then when they're done with thinking, they try to pick up the chopsticks next to them and try to eat something, and then they want to continue with thinking. Now, it could happen that their neighbor has picked up the chopsticks already, so they have to, if the chopstick is already in use, then they have to wait for some more time and then try again. So that's the model of these dining philosophers. So think for an individual actor, thinking, waiting for the chopsticks so that they can start to eat something and put down the chopsticks again, and then go into the thinking mode. And whenever they start eating, so when they finish with thinking, they can produce a snippet of wisdom for the world to consume. How do we implement this in our example? So we have a range of components, and some are actors and some are not actors. So some are just plain OSGi components, like one bundle encapsulating all the system infrastructure. We have one service that produces wisdom, so you can call it and get a snippet of wisdom, just a line of text. Then we have the dinner, that's the core component which starts up the whole system. The dinner will make sure that the actors get fired up and started. Then we have 4 components representing the actors of the scenario. One is the table around which the philosophers are sitting. So one table actor, we have a number of philosopher actors, and we have a number of chopstick actors, and one scribe. The scribe is used for the philosopher. When they finished with thinking, they just tell the scribe to publish the wisdom they've generated, and then the scribe can do it at their own leisure. Just so the philosopher doesn't have to wait for the scribe. And this is all completely asynchronous, but the way these things are connected is that the dinner one uses this service from the table component. So there's a factory service that creates the actors, and the table actor again uses services to create the other actors as needed for the scenario. And these are all OSGi services which are injected. So they're all, the construction is completely by injection. So for instance, for the dinner component, which was a plain component, non-actor, it's simply, there's an injection during the activation, in the constructor of the system. That's the supporting libraries and the service that will give it the table actor. And in a similar way, this philosopher implementation of the actor service, which is an actor, they also, the wisdom generator, for example, is injected here just as a normal OSGi service for consumption during the message processing. So that's all done through plain OSGi means. And then at runtime, what happens is that the dinner component, which is the first one to fire up, when the example fires up, it will spawn this table actor, and the table actor, when it processes its first message, will spawn the other actors as needed. So in this concrete example, it would spawn 5 philosophers, 5 chopsticks, and 1 scribe actor. And then the actors would start exchanging messages. So the dinner component sends this message to the table actor that's created. So this is a non-actor component, but it can talk to actors. So first of all, it can spawn the actor and get its address, and it can send it messages. So it sends it messages, please host a dinner. Then the table actor knows, okay, now I should spawn these other actors, and they will start doing their thing. And here you can see a more complex exchange between these actors. So the philosopher will send a take message to both chopsticks, and depending on what they respond, either taken or busy, the philosopher will go to the next stage of either thinking or eating or waiting again. And at the end, it will send the put message back to the chopstick when the philosopher is done. And that's 5 philosophers doing it all in some sequence. And when the philosopher is done with thinking and is ready to produce wisdom, they send a write message to the scribe, and the scribe will output the wisdom to the outside world. And the philosopher has actually used a call to the outside system, to this non-actor service to get this line of wisdom to produce. So, and these are also special constructs because they are supposed to be asynchronous, because the whole actor processing rests on the approach that message processing should never block. So the philosopher, when they're processing, for instance, any message, they would never put out system out print line and wait for the print line to happen, because it could involve some kind of I/O that's blocking or never comes back or so on. So the idea is always to wrap all this into asynchronous calls. That's where we use the promises, the futures that we have, the API, and to just not wait for it to happen, simply to continue processing. So here you can see how the spawning the actors works. So here we have the dinner component, which was not an actor, but it uses the injected actor system to spawn this table actor by using this create method of the table service. So here it's calling the OSGi service and using it to using the injected system service to spawn an instance of the actor, and all this is wrapped into promises, into the Java future API in this case. That's given by the Akka implementation of actors. So they use this API. They're not OSGi, or they're OSGi agnostic, and there the dinner component waits for the address to be returned finally, so that it can continue sending messages. And you can see here how message processing works. So here we are inside the table actor, and the table actor, when it receives the host message from the dinner component, it will also spawn the chopsticks. So that's the table actor's role of creating all the whole scenario, consisting in this example of 5 philosophers, 5 chopsticks, 1 scribe. So here you see the snippet that's creating the 5 chopsticks.
The context is Akka context?
Yes.
Or OSGi?
No, that's Akka. So this is a Akka specific. This sort of style, this pattern is Akka. How do I process messages in Akka? It looks a little complicated, but not really. I don't know. In Scala, it looks a little more elegant. In Scala, you have the advantage that you can do pattern matching, which is not so expressive in Java. But this is kind of the pattern. This snippet of code is looks complex, but it's just the loop that creates the because it's not just creating one. So this would be a very simple message sent to the. So this is where the dinner creates the table object. Here is just sending a message. The actor lingo is tell. So the command is tell. So it's telling the table to host the message, and the message is a specific Java object. And we can look at the code in a minute. We can see a little more detail. And this is how actors exchange messages. And here you can see a little more how an actor is constructed. So the actor is defined by defining behaviors. And the behavior consists of reactions to messages. So here we have 2 behaviors. One is called available, one is called taken. So they represent the states of the actor. In this case, it's the chopstick itself. So the chopstick has the state being available, put down, or having been taken. from the table. And it will respond differently to the same take message. So if it's available, it will reply, yes, I'm taken by you, or it will reply, no, sorry, I'm busy. So this is sort of the pattern how messages are processed and exchanged and how they are bound to behaviors. And this would be an example of an actor communicating with the outside world, with a non-actor world. So here we are again within a behavior. So this is the behavior we're waiting for the other chopstick. And we're getting the message from the other chopstick, yes, you've taken me. And now it will create an asynchronous future with the code to generate this snippet of wisdom. So it's simply calling the wisdom service, the injected one. And then it's after that has completed, the scribe will be told to write. It will receive a write message to output that message. So this is all wrapped into a completable future. So the message processing is finished. So it will just immediately continue. So the actor will be ready for the next message, but it will have sort of fire and forget these actions. You could even say that this future is itself a kind of one-time actor, a very lightweight actor that's being created on the fly. Okay, so if there is time, we could look at code, which is always a little awkward here because so first of all, I would like to run the code. So just to prove that it's running. Oh, sorry, I forgot to turn on the mic. Okay, so here it's difficult to see even from the front probably, but you can see here the actors outputting or logging their activity using an Acker facility for logging. So this again asynchronous, so the message processing doesn't have to wait for the log to be output, but here you can see the actors doing their processing, and from time to time you will see an actor outputting some wisdom, and at the end there's a timeout, which simply means that the dinner is forcefully ended. So what happens is that the table actor sends itself a message. I hope I'm correct. We had different ways of choreographing this, but anyway, so there is a timeout, I think, by sending a delayed message, a timed message to the table object itself, and just to stop at some period of time. So there's no logic when to stop the dinner. It just simply stops it after a given time. And that's, I think, not so significant here. But you can see, so here I'm just, let me see if I can help here. Can I do this? Excuse me for being so dense here. I want to try to show the shell. So let's move the magnifier to the shell, I'm not sure. So we have the shell running here, and what I could show, I could restart the whole exercise by, I didn't rehearse really using the magnifier properly, sorry, excuse me for this. But what I can do, I can just stop bundles and restart, for instance, the dinner one, which is supposed to start the whole system, but it won't start because one of the other services is down. As soon as I start that service, again, processing will restart because, sorry, no, this was not the wrong sequence, that was the wrong sequence, but So I'm trying to start the dinner bundle again, and it will start, but it won't start until all the services are available, and then the whole processing starts afresh again. So this is just to show that this is all regular OSGi life cycle of services, and that the actor system can deal with that. So if we look a little at the code, so let me see if the magnifier helps us here again. So here we're looking at the chopstick class, and the chopstick class, the API class, so again, that's perhaps also important to mention. We separate, for a good service, we have an API, we have implementation. So this is the API of the chopstick service. It has this create method for creating an actor. It has an interface that defines the interface that defines the messages. So the chopstick interface, so the command interface defines classes which are the message objects being exchanged. So they can have parameters, so depending on the semantics of the messages. But in all, this describes the actor, the chopstick actor, the create method to create them, and the messages that can be exchanged. And then we can look at the some implementation. So we could look at the dinner class. So here we just have the constructor, and that already with all the injected services, and it simply fires up the whole system. And as we saw, there was this code that would spawn the initial table actor, which leads to the other actors being created. But perhaps it would be good to look at the philosopher implementation. So this is probably the most complex actor, which is because it has quite a few states. So you can see here that we have quite a few different behaviors depending on which state it is in. So it could be just seated, it could be they've just sat down, or they're thinking, or they're hungry, or waiting, and inside each of these behaviors there is this message processing that you saw on one of the previous slides. So this is the very actor-specific coding and the flavor of coding, but it's important to realize that there's no state in the actor proper. So there is the ejected service, that's true, but that's just happens once. But all the rest of the processing is the only state is in which behavior is the behavior registered with the actor runtime system. So which is the next behavior that's going to be executed when a message arrives. There's no internal state members or anything.
So does it keep state in the actor context, if it needs to know information between messages? For example, a philosopher needs to know which two chopsticks he should be reaching for.
Right, so that's all encoded in the behaviors. So here you have you're thinking, you're hungry, you're waiting for one.
Right, but I need to know which two chopsticks. There are 5, and I can't reach the one across the table. So which two chopsticks are the ones I should reach for?
Right, and that's encoded in the parameters of the behavior that you're creating. So it's like a continuation. You know, anyone who's familiar with using continuation functional programming, you just add this parameter to the call of the behavior, and then it lives in there in this behavior object. So you could argue that the behavior objects carry the state. So there is state. So there it would know which chopstick was the one it had already picked up. Okay, not sure what I should be showing here. I don't think I should be showing any more. So just let me leave this and go back to the slides here. So now let's go back to extend. So is it managing, or do I need to? This is the risky part, switching between different states. So extend, that's where I want to go. Extend, that's what I want. It's not showing down. Okay, so let's do it differently. Let's go to duplicate after all. Then I need to somehow get rid of this and just restart at the place where I wanted to go. So, okay, so the findings. So we found, yes, it works. We can construct a system in this way. We can use actors in OSGi, and it feels quite comfortable, especially because this injection of the services works quite well. We feel it's quite modular in the sense that we have a good separation. So we have API bundles for the actor APIs. We have implementation bundles. We can, it feels just like when we construct other services as well. We have completely asynchronous communication. So within the actors, that's sort of the natural way that you would do it in Akka, within the actors. But when you sort of communicate between the outside world and the actors, it also feels correctly asynchronous, but it is, you do have to do some special wrapping. So what you can't do, or what you're not supposed to do, is in the message just do some synchronous call to some service. So you would always wrap it into into a future, into a promise, and make sure that it doesn't block you. But that works, and it works sort of so when the non-actor part of the system wants to communicate with the actors, it's just done by messages, and the other way around is done by synchronous calls wrapped into these futures. So that does work. What is a special case is that how do you handle the OSGi dynamics of which the actors, once they've been created, know nothing of? And there's some special code which is wrapped around the message processing to make sure that when an actor dies or is supposed to die, that that is appropriately handled using the Akka mechanism. So there's something like a death watch. So you can watch out. You can watch actors and you can watch their life cycle. So it's kind of attaching the actor life cycle implemented in Akka with the life cycle that we know from OSGi services, where you when a service dies, you want to make sure that the actors flying around also get killed. Sorry for that terminology. Okay, so that's something special. There's more to that, but that's part of the RFP 195 work. So Akka provides persistence. So you can, when the actor system goes down, you can restart it from the state the actors were in. If you use the sort of the persistence mechanisms, that's something, well, we also did some work on, but not in this demo. And there's a supervision mechanism in the Akka system also. So the expectation is that every actor has a supervisor that created it, or it's attached to a supervisor, so that there is some control over when something goes wrong. So not when the actor dies so much, but when an exception occurs during processing of a message. What happens then? And there's a way to catch the exceptions during message handling by this supervision mechanism. Okay, and we found, well, there is some boilerplate code, so if we could look into the code, especially this wrapping of the death watch mechanism around the actor creation. That's a little boilerplate code that could go away if we said, let's implement an actor system sort of as an OSGi spec that would not include such code. So in that sense, it's well, it's more than a prototype, but there's still some boilerplate code that we would like to figure out how to make it go away. Okay, so that's it, what I have around this. I hope I've been rather quick because I was concerned about the time, but I didn't get a reminder.
Do you have some time for questions? If any questions for Udo?
So please. Remarks, comments, any reactions?
No, then please join me in thanking Udo.
Yeah.